Okay, so today let's talk about the negative and zero rules for exponents. So in our TOC, we're still in Unit 1, zero negative exponent laws. I'm starting on page 9. If you may be starting on a different page if you've taken more than one page to do your notes beforehand, and that's fine. So go ahead and write that in your TOC. Okay, I'm actually just going to write it on a flat sheet of graph paper for you guys. So at the top of your page, I want you to write the zero rule, and the negative exponent rule. Okay, so we're going to come back to those in just a minute. Down below, I want you guys to actually insert a table. So our first column is going to be called exponential form. Followed by expanded form. And in the last column, standard form. And 3 to the negative third. 3 to the negative second. 3 to the negative first. 3 to the 0. 3 to the first. 3 to the second. And 3 to the third. And we can go on, but we're just going to stop there at 3 to the third. And we've actually had some of these numbers in a table previously. So we should know that 3 to the first means that we just have 1 3. So that standard form number would be 3. 3 to the second means 3 times 3. And 3 times 3 is 9. And 3 to the third means 3 times 3 times 3. And that should be 27. So we should notice going upwards that each time, each row adds an additional 3. So in other words, going up, we're multiplying by 3, right? So if going forward means we're multiplying by 3, moving backwards through the table would mean that we're dividing by 3. So 27 divided by 3 would give us 9. 9 divided by 3 would give us 3. Just as 3 times 3 would give us 9, and 9 times 3 would give us 27. So let's say we continue to go backwards, right? If we divide by 3 going backwards, 3 divided by 3 would give us 1. If we divided by 3 again, we'd have 1 divided by 3, written as a fraction. If we continued to divide by 3, we'd have 1 divided by 3 times 3, or in other words, 3, 1 to the 9th. And lastly, if we continue to divide by 3, we'd have 1 to the 27th, or 1 divided by 3 times 3 times 3. Okay. Now you notice I didn't put anything here next to 3 to the 0 power. And part of that is when we think about inverses, right? Going forward, multiplication, going backwards, division. Those are inverses to each other. And the other day we talked about the additive inverse and the multiplicative inverse. And with additive inverses, our goal is that when we add two numbers together, we would create 0, or it would equal 0. So 3 plus negative 3 would equal 0. 4 plus negative 4 would equal 0. Negative 5 plus positive 5 would equal 0. But that's on the adding subtracting side. When we're multiplying or dividing, we don't look at our starting point as 0, partly because anything multiplied by 0 would just be 0. We wouldn't have anywhere to go. So our goal when we're using a multiplicative inverse is to reach 1. Why? Because if you add or subtract something with 0, it doesn't change the value. And on the multiplication division side, if we multiply or divide by 1, it doesn't change the value. So this also would be 1, because think about it, it can't be 3 because we have 0 3s. So we're starting at 1. The other thing we should notice is that these numbers are multiplicative inverses to each other. So the opposite or inverse of 27, what I like to call the refliprical, is 1 over 27. The opposite or refliprical of 1/9 is 9 over 1, right? And even though this says 9, we should know any whole number can be put over 1 to make a fraction. So what does that mean? Like, what does that mean in the context of the 0 rule and the negative exponent rule? Well, for the 0 rule, it means any base to a 0 exponent will equal 1. In other words, symbolically, a to the 0 equals 1. Conversely, 1 over a to the 0 equals 1. Because a to the 0 equals 1, 1 divided by 1 is still 1. Okay. The negative rule, because in math, our simplification process is, unless they say we can leave it in exponential form, we can't have any exponents, right? So we have to be able to get rid of the negative exponent. And more importantly, in math, we prefer positives to negatives, so our final answer should really have no negative exponents in it. So to eliminate the negative sign of an exponent, the base and the exponent flip over the fraction bar. So how do we represent that symbolically? What we know is that a to the negative n is equal to 1 over a to the n. And if you think back to our table here, 3 to the third was 27, but 3 to the negative third still had a 27. It had just moved to the bottom. And in the bottom here, we don't see negative exponents. We just have 3 to the first times 3 to the first times 3 to the first. And you can see that pattern throughout the table, right? Here, here, and here. And then 0, of course, is neither positive nor negative. So a to the negative n equals 1 over a to the n. And conversely to that, 1 over a to the negative n would equal a to the n over 1, otherwise known as just a to the n. So let's go ahead and do a few examples, kind of solidify our understanding here. Push this back up. So some examples. So we know 2 to the 0 is equal to 1. We should also know that m to the 0 is also equal to 1. So that rule for the 0 rule applies to both fixed numbers as well as variable bases. If you think of the law that we recently studied, the product law, if we had 2m to the 0, right, that 0 would distribute to both of them. Right now, they both have exponents of 1. So 1 to the 0 would be 0, 1 to the 0 would be 0. So this actually just winds all to be 1. When we think of some negatives, if we know 2 to the negative second, right, to get rid of that negative, I have to take the base and flip it over the fraction bar, and then it maintains the same exponent, but the sign has changed. Instead of negative, it's now positive. And I need something on top, so it's a 1. And 2 squared, or 2 times 2, we know, is 4. That also holds true for variables. So if I have n to the negative third, my base is n, it would have to flip over the fraction bar. It would maintain its exponent, except the sign has now changed from negative to positive, and I have a 1 on top. So the opposite of that, 1 over 2 to the negative second power. Again, I'd have to flip over the fraction bar, the base, and the exponent stays the same except the sign changes. So 2 squared would be 4, or just 4. And 1 over negative n to the negative third. So flip the base over, change the sign, and anything divided by 1 is itself. So exponents are actually another way to represent numbers. So the number 4 could be represented as 4, can also be represented as 2 to the second, or as we just learned, it can be represented as 1 over 2 to the negative second. All these three numbers have the same exact value. Okay, so again, these are the 0 and the negative exponent rule. We're going to go forward and do the guided practice in our digital math interactive notebook. And these are your notes for today.